today we're going to talk about correlation. All right, so first, let's go back and just briefly review summarizing scatter plots quantitatively and talk about all the other things we've talked about with scatter plots so far. Then we're going to talk about eyeballing the coefficient, the correlation coefficient, or what we call R, Pearson's R. Because actually, if you have a set of data that looks a particular way, often you could sort of ballpark where the correlation coefficient probably falls. And then we're going to talk about precisely calculating it. Then we're going to go back and talk about the relationship between R and B1, or slope, of our regression line. All right, so first let's talk about summarizing a scatter plot quantitatively. So shape we didn't deal with. We just looked at it and sort of said, maybe that's pretty good. And we'll talk more about shape in the next couple of lessons. But for now, we're going to leave shape alone in terms of quantitatively calculating it. But we did look at how to precisely calculate the trend, or by looking at the regression line, sort of that middle line in between all those lines that summarizes the middle of all those points. And that middle line really gives us the relationship between x and y, because it's a function that gives us, if we have x, we get y. If we have y, we could get x, right? So we could get the relationship between those two variables. And then finally, today we're going to talk about calculating strength. Not just looking at it and sort of saying, oh, it looks pretty strong, right? But instead, we're going to actually calculate the correlation coefficient, R. And really, that idea is simply how packed around the regression line is our data points, right? Are they tightly packed? Is it a strong correlation, like it's strongly packed around around that regression line? Or is it very loose? Is it very dispersed, where you can't really, it's not really sticking close to that line? Then we would have low strength or low correlation. All right, so first let's talk about just eyeballing it. Now, for a lot of data, you might have no relationship between two variables. And in that case, the spread should look something like this, where there's no real line in there. It's just sort of this fuzzy cloud of dots, right? And remember, each of these points are a case. And each of those cases have two variables. And one variable, x, is on the x-axis. And the other variable, we'll call it y, is represented on the y-axis. So that point represents x here and y here, right? Now, in this case, there's no relationship between x and y. Just because you know what x is, let's say we know x is here. Do we have any certainty as to where y might be? Well, not really. There's some y's down here, some y's up here, right? And even more so, what about if we thought x was here? Do we have any reason to say y is in a particular place? No, not really. And so because of that, a line won't help us here. A regression line doesn't actually summarize this very well. And it's because the correlation coefficient is very low. There's very low strength. There's very low adherence to the line. Now, moving out a little bit further, you see that this one is starting to have more of a sort of elongated shape, right? And this is still a fairly low correlation, but you could still see that there's starting to be a linear relationship between x and y. Namely, as x sort of goes up, y also goes up. So this is what we call a positive correlation. So there's a relationship between x and y that's linear and positive. Excuse me. Notice that right on the other side of this is the exact opposite, where it's the same shape, but it's been almost like flipped around, like as if we put a mirror here and looked at the mirror reflection, right? And in this case, it's the same shaped cloud, but now as x goes down, y goes up, right? So here we see the opposite relationship between x and y. And that's what we call a negative correlation. And because of that, the signs act accordingly. Here, the sign for this slope, for the slope that's negative, is negative 0.4. Here, for a slope that's positive, as x goes up, y goes up, as x goes down, y goes down, right? That's a positive number. And so we could easily, just by looking at the correlation coefficient, immediately know what kind of, roughly what kind of relationship x and y have, right? Now, notice that as we go out even further, not only do the numbers get bigger, right, bigger out from 0, right, but the numbers correspond to how liney the data are, how much they correspond to a line, right? And so it's not really about having more dots or less dots, but it's really about how much do all those dots fit to a line, right? And that's why we often call it fitting the data to a regression line, right? Because we want to see, is it a good fit? Is it a bad fit, right? And correlation coefficient gives us the strength of that fit. Is it a really strong fit, or is it very weak and loose, right? And the actual maximum for a correlation coefficient is 1, and the minimum is negative 1. And that's as far as it will go. You can't have a correlation of like 1.1, right? And we'll talk a little bit about why. Now here, what you see is that this might have the same number of points as all of these, but it's just saying that there's very, very little variation from the line, right? So there's not a lot of variation out from the line. Whereas something like 0.8, you could see, it's better than 0.4, but it's not quite as liney as 1.0, right? And so that's one way you could just very quickly eyeball correlation coefficient. You could just look at a set of data, and as long as it's sort of elongated a little bit, maybe it's a 0.4, but if it looks, like a sort of tighter ellipse, maybe it's about a 0.8. And if it looks, very, very close to a line, perhaps it's close to 1. It's very rare that you get like 1, though. All right, in real data at least. But I want you to notice something. Correlation coefficient, other than caring about positive and negative slope, it doesn't otherwise care very much about slope. For instance, look at all of these situations. These are all lines, right? They're all very, very liney. They're maximally liney, right? Notice that these lines all have the positive slope, right? But they all have the correlation coefficient of 1, right? It doesn't matter whether as x changes, y changes very quickly, or as x changes, y changes very slowly, right? So the slope doesn't matter, except for just the positive or negative part, right? Same thing with the negative slopes. Even though the slopes are all different, they all have a correlation coefficient of 1, right? Now, there is an exception to this rule, and it's this line right here, the perfect horizontal line. Now, let's think about what the equation for just a regular horizontal line is. In a regular horizontal line, it doesn't matter what x is, y is always the same. So let's say here, like something like y equals 3, right? So that would be like a horizontal line, or y equals -2, or y equals 0.1, right? So those are all examples of horizontal lines. Now, let's think about in the case of a horizontal line. It's sort of perfect prediction, right? Because no matter what your x is, right, you could tell me whatever x you want, I could exactly tell you the y, because y is always in this case 3, right? And so it's perfect prediction and it's perfect lininess, right? But the correlation coefficient is 0, right? And it's and we'll try to figure out why that is for horizontal lines as we figure out the formula for correlation coefficient, and that hopefully that will become more clear. want you to see there are many, many ways in which data can have seemingly no linear pattern or very weak linear pattern, because that's what the correlation coefficient tells us. So if we see, our data has a 0 as its correlation coefficient, do we know that it looks just like a cloud? No, in fact, it could look like any one of these crazy shapes down here. All of these distributions, all of these scatter plots have a very, very weak correlation. Because remember, correlation just means how liney is it. This one's not liney, this one's not liney, this one's not liney. None of these are very liney, right? Even though some of these have very, very regular shapes, right? Correlation coefficient can't tell you that this has an interesting shape. All it tells you is whether it coheres to that regression line or not, right? And so although these are very interesting sets of data, for instance here, there's sort of 4 rough clusters, right? And even though we could sort of see that when we just eyeball it, the correlation coefficient won't tell us that. Or in this case, this is sort of odd data set, but even here, the correlation coefficient won't tell us that either. And so for all of these data, the correlation coefficient is very close to 0. So I want you to see, there's many ways in which you could have a correlation coefficient of 1 or -1, and there's many ways in which you could have a correlation, coefficient of 0, right? Just because we get the correlation coefficient doesn't mean we could see the shape of the distribution. That's why it's often useful to do a scatter plot anyway, just even for ourselves, just so that we know what our numbers are probably going to be describing. All right, so let's say we have this graph, and this shows us this nice correlation. It looks probably pretty high, like maybe something like R equals 0.8. So closer to 1 than to 0, but maybe not quite 1, right? So this is a pretty good correlation. And you might have 2 variables here, like for instance, perhaps this gives us the z-scores for some variable, like perhaps we're looking at twins and we want to know, does the intelligence of one twin, does the IQ of one twin help us predict the IQ of the other twin, right? So maybe it's true. Maybe that does seem to be the case. So here we might put something like the intelligence of twin 1 on this axis, right? And then we'll put the intelligence of twin 2, their z-score from their IQ score. We'll put that on the y-axis, right? Now, when we have these scatter plots, it's very important that we don't lose sight of that we could sort of toggle between the trees, the individual little dots, and the forest, the big overall pattern. When we look at correlation coefficient, we're sort of looking back. We're sort of getting a bird's eye view and looking very far away and sort of trying to see the overall pattern, right? And that's sort of the forest, right? But it's really important to remember, what are my trees? What are my cases, right? It's important to remember what this dot means. So that's what I mean by the trees. Like, you want to remember, what are your cases? What are your variables? That's always step 1 of looking at a scatter plot. And so in this case, it's not that each of these dots represents just one twin. It's that these dots represent a set of twins, a pair of twins, right? So here, this represents both twin 1, who's a little bit below average, and twin 2, who's actually a little bit above average, right? And so let's pick out another one. Let's say this one. This twin is a little bit above average. And guess what? So is their twin, right? So their twin is also a little bit above average. So each of these dots actually represents 2 people in this case, right? A set of twins. So you want to be able to switch your perspective and sort of zoom in and see the trees, but also zoom out and see the forest and try to estimate things like correlation coefficient, or even try to estimate, let's say, the regression line, to try and eyeball where that might be.